All right, so last week we did a hopefully fairly thorough review, but it wasn't really that thorough. It was very skimming the surface of a bunch of topics from 210 and 211. So I'm hoping that people feel caught up. They've shaken off some of the rust, the programming rust that accrues as soon as you stop programming for even a day. And we're ready to get back into some of the more complicated topics as you start transitioning. I think 212 is really the trend. 212 and 300 are both transitionatory classes where you go from solving smaller problems by yourself to starting to think about how do I interface with other people to produce large scale software that is bigger than something that I could produce by myself. And that is what is the sellable skill that you're going to have if you graduate with a computer science degree. It's not what you individually can do, but what you can contribute to a group. And this is where you start really transitioning and figuring out just how different that is from the process of solving things by yourself. Not to say that solving things by yourself is not a good skill to have. It's an excellent skill to have because you're going to need to be able to produce your component, but being able to interface your component with every other requirement around you in a large scale project is not easy. Not easy at all. So we're going to spend this week talking about testing and getting you set up to start writing unit tests in your own classes that you write. Before we start talking about all of the problems that you can introduce into your code when you're doing advanced object-oriented programming. So, motivation for testing, I sit down and I just code out a small program. How do I know it works? What process would I need to go through to know, yes, this program solves this problem, or no, this program does not really solve this problem? There are lots of different ways that I could do this, but what's one such way that I could do that?
Printing.
Could print some things. Imagine I wrote just about the simplest program that I possibly could. I wrote down, all right, it's just going to be a method. It's going to take in two parameters, A and B, and it's going to return the sum of A and B. Very simple program. How can I be sure that works? I could start printing things, but what should I be testing? What are the appropriate test cases?
Good morning.
Yeah, you could look at the code and see, is the one line that you need to add two things together actually there? But think about it from a bit more of an abstract perspective. How many different possible, let's just assume positive integers for the moment. How many possible positive integers could I have between these two parameters, A and B?
The sum must be greater than either A or B.
As long as they're positive.
Yeah.
Yeah. But to exhaustively test and print every possible solution, I would need 0 plus 1, 0 plus 2, 0 plus 3, 0 plus 4, 0 plus 5. There'd be a nearly infinite number of those. Assuming it's an int, I can stop at 2 point something billion once I reach the maximum value that can be stored in an integer. And then I'd have to loop back around and try 1 plus 0, 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4. How many tests is that? How long am I spending verifying my program? More time than I have left to live, probably. I could pass this on to my descendants. Be like, I started this problem back when I was in my 30s, and I need you to finish it off for me because I'm gonna die before it can possibly finish. That seems unwieldy. But do I really know that it works before I've tested every single one of those inputs? Can I be absolutely sure that it works? I'm going to leave that as an open question for a moment for you to think about as we go through the rest of this motivation. So we've defined kind of how I know it works, but what do we mean by it works?
Returns the answer you're looking for.
It returns the answer you're looking for. My favorite one is the professor didn't find the bugs that exist in my program, so it works. So here's what we're going to mean by it works. If it produces the correct output for every possible input. How could this be verified? We talked about printing it out for every possible input-output pair. That sounds gross. That's a lot of manual time. Could I write a program to verify my program? You could do something like between integer.min value and integer.max value for each of these possible ones. So throw it in a nested loop. And for each one of those, you would assume that the output should be the sum of those two numbers. So you could go through and verify that your program produces the appropriate output for every possible input pair. Since there are a finite number of those in how we're storing integers in computers. Have we seen that before, the limits of integers? Yes, no, I see some people raising their heads. Raise your hand if you've seen or heard of the limitations of storing of integers. Could be worth going over briefly. Is there a question or comment?
I was just gonna say, in order to figure out what the desired output would be for the unit test, you have to sum it as well.
Yeah.
Like using the same code.
Yeah, well, yes, for something that's simple like that, the verification is part of calling, yeah. That creates kind of an interesting, you're defining the word by using the word. Interesting recursion there. So yeah, the limits of integers. So we discussed, I think, it was briefly mentioned in passing in the last class, that the space that we have for storing an integer is limited. Who knows how an integer is stored internally?
Each bit represents 2 to whatever power that bit is, if that makes sense.
So here we have the 32 bits that a 32-bit machine will use to store an integer. Each of these dashes will be a 0 or a 1, but it's stored in what's called 2's complement. Has anyone heard of this concept of 2's complement before? What was 2's complement? It was very different from this concept of sign and magnitude. So I think what was kind of being described before is you had a sign bit followed by an amount that things, so this is stored in binary. Are we familiar with binary arithmetic or binary numbers and what they mean, how to convert binary to decimal, vice versa? So if I put a bunch of zeros up here and then 1, 1, 0, 1, that would represent what value in base 10? 13, that'd be correct. This is the 1's place, the 2's place, the 4's place, and the 8's place. So this 13 is just 8 plus 4 plus 1, or I guess you could say 1 times 2 to the third plus 1 times 2 squared plus 0 times 2 to the first plus 1 times 2 to the 0. You could turn this into an expression that's based on powers of 2, which is really how we define binary. So that's how you go about that conversion to get the 13. Now that I think we get that, the whole purpose of this is how we store numbers. So one intuitive way that people like to come up with this is we dedicate this bit to represent either positive or negative, and the rest of this represents how big the number is. There are two massive problems with this. Anyone know what those problems are?
When you go to the max number and go +1, it will flip the first bit.
You get some really strange, yeah, like for instance, some really, really large number, large positive number, +1 is a really, really, is basically it's 0. You don't loop around to the large negatives and then work your way back towards 0 like you do in 2's complement. You get 0 representing positive, something large, this rolls over to this 1, and then you get 1, which means negative, followed by a bunch of zeros, which indicate 0. What about 0 followed by a bunch of zeros? What number is that? 0. So we end up with this really weird, there's a positive 0 and a negative 0. Depending on what the value of this bit is, if all of these are zeros, this bit can either be 0 representing positive 0 or 1 representing negative 0. That's weird. All right, what's the other issue? If one number is negative and one number is positive, and you try to do something like add them together, what happens?
It subtracts.
It does something really weird. So let's just assume we have some very simple 3 with a sign bit. Let's do positive 0, 1, 1 and negative 0, 1, 0. What should this mean to add? We're going to do the sign and magnitude. This is positive 3 and negative 2. If we were going to say this is positive, 2 plus 1 is 3, negative 2. By sign and magnitude, again, this is not how this actually works, but to just show why this intuition is really weird, if we go through this process of trying to add each one of these together, 1 plus 0 is 1, 1 plus 1 is 0, carry 1. What's the answer?
5.
Yeah, this says 0 plus 1 is 1, so we got negative 5. Is that the right answer? Absolutely not. So this concept of sign and magnitude falls apart as soon as you get over the intuition of, well, that makes sense. You try to do math with it and it stops making sense. All we need to do to make this work is instead of defining 1 followed by a bunch of zeros as negative 0, which there's no such thing as negative 0, but we could define this to, instead of being a small negative number, be a large negative number and count down. So now this would be some high negative number, and 1, 1, 1, 1, 1, 1, 1, 1, 1 is going to represent negative 1. And then you convert this into a 0, and you get negative 2. 0, 1, you get negative 3. You start counting down as you start counting down the negatives, negative 1, negative 2, negative 3, etc. Does that make sense? You get this really interesting, intuitive way to think about numbers. I like drawing this out with 3-bit numbers. You basically get an intuitive version of 2's complement, where let's have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Where do I want this over here? I want this over here. All right, according to 2's complement, what is each of these values? We know this is 0, this is 1, this is 2, this is 3. This is negative 1. This is negative 2, negative 3, and negative 4. This kind of shows us why there's one more negative number than positive numbers, because 0 is considered to be a positive number. How do we convert from something like inverting? Do we remember the rule for inverting in 2's complement? If we have positive 1 and you want to figure out how do I represent negative 1, Or if I have positive X, you want to be able to represent negative X, what's the rule? Yeah, flip it and add one. So to go from positive to negative, you flip all bits and add one. And going from negative to positive, you also flip all bits and add one. If you visualize things in this radial way, it actually makes perfect sense. If you want to go from 3 to -3, you flip the bits, and by flipping the bits, you're going to go directly across the circle. And then to add one, you're going to go in this direction or this direction. So you flip the bits and add one, and you get over here. How do we flip the bits? From 1, 0, 1, we get to 0, 1, 0, so we go across and we add one. So you produce this really strange, interesting, slightly going across, and you produce a little figure 8, which is why when you flip the bits and add one and flip the bits and add one, you get back to where you started. So this is the most intuitive diagram I've ever come up with for explaining the concept of 2's complement, but this is how binary arithmetic works. So if you're able to kind of visualize this process, I think things like binary addition, binary subtraction become more intuitive or make more sense. Total aside from talking about testing, but since people hadn't heard of some of this, I think that helps with. Once you get to discrete, or if you're in discrete right now, this visualization makes beginning computer science type discrete with binary makes so much more sense. All right, the whole point of this is how we store integers internally. Today's class is very much like a stack for those of you in data structures. We're just new topic, new topic, new topic, slowly backing out of those topics as we, anyway. So this is how we store integers internally, and this could be verified by coming up with every possible set of integers, since there are a limited number of bits that we are storing these in 2's complement. So you could do that. So is it enough to try a single input and verify a single input? Or 2 inputs, or 10 inputs? Is there potential logic where if you could test the first 10 of these, would you know that the program works? So I wrote a program, I'm gonna hide the source code from you. It's your job to give me a list of test cases, and then I will give you the result of what my program does. And your job is to tell me, yes, your program works, or no, your program does not work. How many of you think you would reasonably need to give me, and what should they be? To be able to tell me, yes, my program works, or no, my program doesn't work. I'll give you an example. So we have A and we have B. We could have 0 and 1, 0 and 2, 0 and 3, 0 and 4, etc., up to 0 and 10. Let's say those are the 10 test cases that I write for this, and this is just, A plus B, and it's a method that takes A and B and returns their sum. If all of these return their appropriate sums, would you buy that my program is correct? For someone who says no, why?
Tested 0 or A.
Yeah, so inside of this sum method, all that exists in there is if A equals 0, return B, else throw some kind of exception that says that I can't do it. Or return 0, or return A, or, yeah, let's do that, else return A. Would that pass all 10 of these test cases? That would. Does this code add 2 numbers?
it's zero.
Does obey at 0, and that's it, right? So what do we reasonably need to be thinking about to test this program? Having some different values of A and not just always testing the same one, maybe adding a negative number to a positive number and making sure that works. When you don't have access to the source, or you're not 100% sure of exactly what the source does, the tests that you write are going to need to be thorough. I've written the test, but then I realized I forgot to implement a couple fairly trivial components. Do I know the values that I tested? Remember, I'm not writing tests at this point, I'm just giving inputs to things. Do we know that those prior tests still work? So I wrote an add function. I produced some test cases, it worked. But now I'm changing the functionality of this to now whatever the result is, I'm going to add 2 to it. Or I'm going to invert it, or anything else that you could do to it. Did the steps that I took to verify the prior program still verify the current program? No, the program has changed. So if I am printing out everything, or I'm going through that testing process myself, every single time I make a change, I have to run all of those tests again to make sure they still work. This sounds like something you really want to do for a homework, right? Just make small changes, go through 100 test cases of it, make a small change, go through 100 test cases. So you have to try every input-output case to verify it works after every single change to the program, or every version of the code that you release. That's not great. This seems time-consuming. So we need some better way to handle this. Real-world applications are evolving on a daily basis or an hourly basis. How many tests do you think need to exist in order to verify something like the entirety of Microsoft Outlook? I can make it worse, the entirety of Microsoft Windows. The answer is an infinite number of cases, but Outlook is updating all the time with new features, changed features, increased security measures, changing how things work in order to keep your information secure from the latest kinds of hacks. Do you really want to run through all of that work of verifying the integrity of Outlook every single time you make a change, every hour? There's more than an hour's worth of testing to do every hour. And it's kind of important if you are Microsoft to make sure that your product works. You do not want your data leaking out to the world from the latest and greatest hack. The monetary repercussions of that would be you're bankrupt very quickly. So you need to be able to verify the integrity of the large-scale programs that you write without going through a disgusting, tedious process. So we don't have time to identify issues manually every time we change our code. We're going to call that committing, because that's what you do to GitHub. You commit your code to GitHub. All right. We're going to define software reliability as the probability that a software system will not cause failure under specified conditions. We want to be 100% sure that the software system will not cause failure under just about any specified conditions that we truly care about. Is that possible? Maybe, maybe not. Is it feasible? Probably not. You can measure this by the total amount of uptime of a software system, mean time until failure. If you have a system that is up and running, how long will it take for the system to fail on average, given an average user load? Any crash data? You make a complex software system, there is a bug in it. I guarantee it. I have a fun one from this morning. Came back from a 3-day break. I did not shut my laptop down. I opened it. It wasn't particularly responsive. Anyone want to take a guess as to the reason that my laptop was not particularly responsive after just being closed for 3 days? Memory leak? You'd be right. What application was responsible for that memory leak? It was actually PowerPoint. It was using 13 gigs of RAM. PowerPoint has a very large development team of very smart people working behind it. That development team on my system could not catch the bug that after just putting my computer to sleep for 3 days, used 13 gigs of RAM, completely unresponsive. So just to give you an idea, bugs are inevitable. It's not something that you can just eliminate, even with the best intelligence out there. Bugs will happen. You want to minimize them. You cannot eliminate them, you can minimize them. Industry estimates of production level code, there are 10 to 50 bugs per 1,000 lines of code. That might seem like software is unreliable, and why would you ever be involved in a system that uses any software whatsoever? Fly a plane, it will crash. Bugs also vary in visibility. Some of them are right up front, staring you in the face. Duh, of course that's wrong. Some of them are incredibly subtle and require extraneous circumstances to even know that the bug is there. So it can be immediately noticeable. Don't even have to run the code, you just have to look at it. It can hide in active code for years until somebody stumbles upon it. This is happening all the time with large applications like Outlook or Windows. They're finding bugs daily. So we're going to define testing to be some kind of systematic attempt to reveal these errors or reveal these bugs in ways that we can eliminate them. A test failing is an excellent outcome. That means you caught something. That's a good thing. If a test passes, then no error was found in the specific situation that the test is testing for. If we want to add two numbers, we need to be able to, in order to test it, provide an associated A and B to be able to test it. We can't go through everything. If we see that a test for A plus B works when A is 3 and B is 6, and the answer we expect is 9, and the answer we get is 9. What does that test tell us? It works for 3 and 6. It does not tell us everything about the software system. It's this very specific situation that we know it works for. And I'm using this example that is very simple for illustrative purposes. I can make this as complicated as necessary to show bugs that are actually reasonable to expect. So this does not mean that no error exists in the system. It just means that this particular test case passes. And what that means is that we need to start thinking critically about what is going to reveal these bugs. What are the test cases? Because you want to find those bugs. You don't want to pretend like they don't exist and just cover your eyes. And if the professor doesn't notice it and I walk out of this lab with 100, then that's great. It was perfect for all intents and purposes. Because that will work while you're in school. And as soon as you're in a computer science industry, that will come back to bite you. So learning how to test well, very important. Testing perceptions. Testing is seen as a novice's job sometimes by certain developers or certain managers. I'll give you a hint, they're idiots. It should be assigned to the least experienced team member to get them up to date on the code because testing is not very important. So they can learn the code if they write the tests for the code. Done as an afterthought. All right, it works. I should write some tests to show that I've written some tests and that this software has been verified. So we'll write the easiest tests that we possibly can to show that we wrote some tests on the most obvious of cases. It works, so great, we can now ship it. That is coding to the tests, or trying to show that you're, how do I want to phrase this? Like showing your intelligence, your average intelligence by talking about the thing you are most knowledgeable about. That doesn't really reveal any information about the state of your intelligence. It just shows that you really know that thing you really know things about. It's kind of the same with testing. If you do it as an afterthought and you write some tests that are obviously going to pass, it doesn't tell you anything about the software system as a whole. It just tells you that it passes the obvious cases. So some quotes that you might get as an afterthought: my code works, it doesn't have bugs, I don't need to test it. You just don't know what the bugs are yet. Or the program is ridiculously simple. I'll just find any bugs by running the program. You have forever to run your program. Some limitations of what testing can show you. You cannot completely test a system. There are going to be so many potential inputs to a system that you cannot verify the associated output. And again, what that means, you need to use critical thinking as you start thinking about what are the tests that are going to reveal the bugs. The testing itself doesn't have to directly reveal the bugs. Maybe it just throws a particular kind of exception, or maybe it gives you a hint that something is wrong. You cannot prove the absence of errors in software by testing. If you're interested in the logic behind this, if you take the compilers course in the CS major, we will actually go over why this is true. Why you cannot write what's called a verifying program. Write a program that takes as input another program and tells you whether or not that problem will finish or that program has bugs. Can't do it. You can look for particular kinds of bugs in particular circumstances. So formal verification, we'll go over formal verification in software engineering and the actual proof behind things like the halting problem in compilers. How bad can bugs be? Aren't a few of them okay? You got close enough. Anyone have any experiences? What's the worst software failure that you have heard of or read about?
Just last night, I watched a video about their Act 25.
Yep. What happened there? Summarize it for us.
It was like an electron beam that was used to cure like types of cancer. So those with radiation in a very specific area.
Yeah.
And it had a software bug that would cause it to not use like a certain type of shield if you hit the up arrow sometimes. And so I was giving people like thousands of times the radiation they're supposed to be given.
Lethal doses of radiation.
Killing them.
Yep.
Crazy.
Is that one of the bugs that's okay in software? Think about the most important software that's out there. What is the most important software that's out there? In your opinion, there's no right or wrong answer here necessarily, but what's important software?
I mean, stuff that like maintains like power grids and stuff like that, because it's so used by everybody and we rely on it so much.
Yes. Anytime where you have kind of a many-to-one interaction, where there's a single software system that affects a bunch of people around that, absolutely. What else? What other kinds of software are really important? Think about life and death, where if this software fails, people are either highly inconvenienced, injured, or killed.
So like traffic systems.
Traffic systems, that can be a pretty big one.
Anything in medicine.
Medicine.
Baking.
So flight navigation and monitoring. You have a failure in that, people can die. Medical dosage monitoring software. If that fails, people can die. Car software, things like the auto brake detection or auto gas detection. Security software for highly sensitive data. How many places have you put your social security number? One of those places should not be in plain text on Canvas. Please do not submit me your social security number at any point. If anyone asks for your social security number tied to this course, it is not me. It is someone pretending to be me, or me having the world's worst and least appropriate joke in the middle of class. Don't do it. But it's also not necessarily in your hands. When you give something like your doctor's office your social security number and they digitize that and they hold it in on their servers, you're placing your trust in them. that their security measures are in place. Because if they do not have good security software protecting that, then your social security number may be gone out there in the world. I can pretend to be you. That sounds like a fun thing to do over next weekend. Some examples of failure. Anyone remember the T-Mobile data breach? If you have T-Mobile or had T-Mobile in 2022, your personal data is out there probably. 50 million users had your personal data leaked and stolen. Oops. Tesla, touchscreen memory issues, 135,000 vehicles were recalled. That's not great. Airbus, we all remember the 2015 A400M that crashed and killed everybody on board. If you want to place a dollar amount to the cost of software bugs just in a single year, and granted, this is an estimate, but anyone know what this number is off the top of your head? $2.41 trillion of damages. So anyone who says that software reliability is just an afterthought or a passing thought, this is our best attempt. Our best attempt at reducing that costs this much money. That's expensive. It's a lot of money. So unit tests are what we're going to be focusing on in this class. There are other kinds of tests as you start to build larger and larger scale systems. We will talk about those kinds of testing in the software engineering course because that has to do with engineering software. For the scope of this class, you're going to still be writing programs by yourself for the most part. And as you're the only developer working on this, the most appropriate kind of test for you will be the unit test. You'll be looking for errors in a particular subsystem in isolation. So you're not going to worry about all the different components that attach to this. You're going to look at a piece of a program and say, all right, I'm going to verify that this piece of this program does what I expect. A unit could be something like a method. It could be a few lines of code. It could be a loop. It could be any small piece of isolated code. So a class, an object, a method, some subsystem that is self-contained. Every language, programming language out there that you might be using will have some kind of unit test tools. The unit test tools in Java is the JUnit library. So we'll talk about JUnit, exactly how to put these tests together. Basic idea of unit tests. For every single class that you write from here on out, you're going to be making a test class that is paired with it. So you make a person object. You will make a person test class that has all of the associated unit tests for the person object. Here's a more generic example. You write a class named foo, you'll make a class called foo test that will store all of your unit tests that deal with the foo object. That makes sense? Any questions about that? You'll write a bunch of different methods in foo test, and you'll be looking for some kind of result. You'll be pairing an input with the expected outputs for that very specific subproblem. That will either pass or fail at all points in time with the current version of your code. You can imagine that I write this test case, I run my program, it passes. I make some changes to my program. The test might start failing because of the changes that I made to my code. But the test will always be there in a way that's easy to run in tandem with a bunch of other tests. So instead of having to run your program and run your program and run your program and feed it a bunch of different inputs and look for the associated outputs, every single time that you make any changes to your code, you can write a test file that has a list of what those intelligent tests are that you can run and get an idea of, I'm reasonably certain my program works because it passes all of these really intelligent and well thought through tests that I wrote for this program subsystem. You're going to be using this assert. Basically, you're going to say assert that these things are equal. Assert some Boolean condition that allows you, you have the entirety of Boolean logic at your hands that says, all right, I want to be able to compare some aspect of my program when I make some assumptions about what the variable's values are. So put assertion calls in those methods to check things you can expect to be true. I expect that this variable and this variable are the same value. That should be true. If they're not true, the test fails. Does this intuitively make sense as to what in a vacuum a test is? We've not yet applied it to any code whatsoever. Just the generic concept of what is a test. So one thing to note about this class, while all of the assignments that you do will be in Java, a lot of what I will give to you will be language agnostic. And what that means is I'm not teaching you to be a Java developer. I want you to be able to go out into the world and write tests in any particular language that you want to. So you should be able to apply this to a Java programming language. You should be able to apply this to the C++ language. You should be able to apply this to Python. Whatever you end up developing in, this information will be valid. That said, for this class, you're probably going to want to tie this to IntelliJ. So how you precisely add JUnit to IntelliJ is following this. And this is mostly just as a resource for people to look up once these slides are posted, because you will want to be able to add tests using JUnit to your own files. So refer to this process, and this can help you get started in IntelliJ. Again, I don't really need to go over it. I will give you a demonstration in IntelliJ at some point if people start struggling with this. But this should get it up and running. If you're going to write a JUnit test class, that class needs to import two things. org.junit.star. We talked about the star being a wildcard before. This just says from the project org, from the package JUnit, import all classes. You also need to import static org.junit.assert.star. And that will allow you to be able to use the assertions that we just talked about. So those two imports go at the top of every test class. So here's kind of what you will look like. You still have the name of the class. So again, if this was foo, this would be public class foo test. Should just be something test. Every test that you write is going to start with @test. And then you're going to write a method that's goal is to test a particular input-output pair. Anytime you have @test, it's flagged as a JUnit test case. So when you go run this file, instead, it's going to be linked to the file that has the same name. So it'll be linked to foo, and it will run through this and run every single method that has @test associated with it. So when JUnit runs your test class, all @test methods will run. If you don't include @test, that method will not be run. It will make it look like your program has no bugs. We'll spend a good amount of time on this slide. Here are all of the kinds of assertions you can make with JUnit. This is just a big dump of all of the possibilities, all of the tools in your tool belt for producing tests. So you can use the assert true method function. So you pass it an associated test, and it will determine whether or not the Boolean test here is true or false. If it's true, you'll get the green check mark. If it's false, you'll get the red X. This would allow you to test. So you put in some Boolean expression in here or run some code, and at the end, you want the result to be true. Assert false is the logical opposite of that. you expect whatever test you write to not be equivalent. So now you will succeed if the Boolean embedded in this test is false, and you will fail if it is true. Why would we ever want to assert false for something? What's an example of something you might choose to assert false? Let's say I have an array list and I want to test my resizing. I could do something like assert false that by adding to a full array list, I do not get some kind of exception thrown. So you would assert false that this particular exception is thrown when I do this associated logic. And that would test to make sure that your array list is expanding when it is full, and you try to add to it. That would be much easier than doing like an assert true that says, if I expand that, then something at the 6th index has something in it. That's a very specific case. Whereas if you check for the associated exception that would be thrown, that's much more general. You're going to catch a lot more errors with that test than a very specific assert true. Assert equals. This allows you to put in an expected expression and an actual expression, and then it will just check whether or not these expressions have the same value. You can assert same. This will check equals equals as opposed to the dot equals. So whenever you have a strings dot equals, you want to assert equals. If you're comparing primitives with equals equals, then you can do assert same. And the reason we might want to assert same, have we seen what happens if we try to use equals equals versus an overloaded equals function on two objects? Do we know what the difference is? It's worth spending the last 3 minutes in class on, for sure. So I have two array lists of values. I have A that points to 1, 2, 3, and I have B, an object that points to 1, 2, 3. These objects are equivalent to each other, right? If we were to assert dot equals on this, so something like A dot equals B, would we expect this to be true or false?
True.
It would return true, right? Because the overloaded equals is going to go through and check each index and assume and say, is A of 0, 1 and B of 0, 1? Do they have the same value for each possible index? What if we said A equals B? Is that true or false?
False.
It is false. The reason being, they're not the same object. They're not stored at the same place in memory. So the difference between this equals and this same, so this does work by equals, but it is looking for it at a shallow copy level and not at a deep object equivalence level. Question?
I was gonna ask if the shallow copy should return true.
Yeah. By equals, which is why it has to specify. So this is an important distinction here. It's asking, are these at the same place in memory? In which case the answer is no. We refer to different locations for each of these. So if we made a change to A, it would not be referred to in B. Now, if we instead point B here at the same object, now equals will return true because it's the same object. And you can have two different references to the same object. Questions about any of that logic? Anything we talked about so far? We will start tomorrow by going over the second half of these because I kind of ran out of time and this was an important aside. But we will probably spend 3-ish days this week talking about tests. And then we'll have some additional time to work on some extra fun programming problems.
So on Friday, you said something about a payroll version giving out extra credit.
Yes.
A completed program. I have all three types on my computer.
Ooh. Send me an email with them and I will take a look.
Okay, sounds good. Why would I find that?
Yeah.
Yeah, it worked out okay.
Thank you.
Thank you.
It didn't just-